Good afternoon. This is Dr. Pradhan here. Welcome to NPTEL project on econometric modeling. So today we will discuss the heteroscedasticity problem. In the last couple of lectures, we have discussed the basic framework of econometric modeling, and last couple of lectures we have discussed various aspects of econometric modeling. Means the aspects means problem aspects. So, like in the last two to 4 lectures, we have discussed the problem of multicollinearity and problem of autocorrelations. Actually, these problems are extra problems related to what we have discussed in the fitness of the model, where we have highlighted briefly, or you can say elaborate way, the specification test and the goodness fit test. So having a specification test or having goodness of fit test is not sufficient to say that the model is best fitted. So even if the model is through specification test and through goodness of fit test, still it is, or it cannot be considered as a best model for forecasting or policy use. So the way we have highlighted few problems already. So like multicollinearity, autocorrelations, and today's discussion is all about on heteroscedasticity. So first of all, what is heteroscedasticity? So the way we have discussed multicollinearity, autocorrelation, similarly we will discuss the issue of heteroscedasticity. It's a very interesting issue, and very important for the econometric modeling. Okay, so because this particular component may be very helpful for cross sectional analysis, also very useful in time series analysis. We have very very beautiful model like arch, gauge, etc. So during that time we will discuss details about this heteroscedasticity issue. So today we will briefly highlight the structure of heteroscedasticity. Okay, so heteroscedasticity is basically the counterpart of homoscedasticity. Okay, homoscedasticity is always positive for the econometric modeling. If anything is directly attached with the homoscedasticity issue, then obviously it is good for the modeling, or you can say it's a very good sign, for positive sign for the fitness of the models. But if there is any question of heteroscedasticity coming into that particular angle, then it is a very problem for the modeling, or it is a negative aspects of econometric modeling. So, to transfer this heteroscedasticity issue to homoscedasticity is the core objective of this econometric modeling. Okay, so means this particular discussion. So now we will highlight what is all about the heteroscedasticity issue. So how we will bring to that particular components. You remember in the last lectures I have mentioned, so far as econometric modeling is concerned, there are 3 aspects. First aspect is dependent classification, independent classification, and error classification. So till now we are discussing one dependent variables, several independent variables, and in the last 2 lectures we have discussed several error terms. In fact, we start with error term 1 u, but within u we will create so many u's. Okay, so if there is any such game with respect to u, then obviously this type this is very interesting problem or extra problem related to this econometric modeling. So today this particular issue heteroscedasticity is purely on error terms, like autocorrelation issue. So the thing is that, so whether it is a bivariate model or multivariate model, so heteroscedasticity is always issue, because it is once you have error terms, so then you will create several error terms, and now there is several different modelings we can build, or you can put a structures so that it can be further analyzed, or you can say you can go for interesting issues, etc. So now so we will see first how it is exactly coming this heteroscedasticity issue. Then we will discuss with respect to its nature, consequences, and its causes, and its detection rules, and also its solution rules. Okay, so first of all, what is all about this heteroscedasticity? Let me briefly highlight bring the issue of heteroscedasticity, then we will discuss details about the heteroscedasticity. So let's take a case of econometric modeling for y equal to say x beta, plus u. Okay, so this is generalized multivariate models, multivariate econometric models by matrix approach. Okay, this is a multivariate econometric model by a a basic econometric approach. So or else you can write like this way. So y equal to beta 0 beta 1 x1 x1 I plus beta 2 x2 I plus continue beta k x k I. Okay, so plus u. Okay, ui. All right. So now obviously this is ui. So last class we have discussed in fact ui. So it can continue like u1 u2 u3 like this way, but first you start with this one, then you first have u, after that you can go for extension of u. So now this particular model can be write like this way. So simply beta 1 beta 1 x1, so beta 2 x2, beta 1 x2 plus beta 2 x2 plus beta 3 x3 plus you can say beta k xk plus u. Okay, so I can write also like this, removing the intercept terms. Intercept term in fact in the deep levels it may have very less impact on dependent variable. So when you have a multivariate models, and when there are k number of independent variable in the system, so that time so intercept has a minor role. In fact, if you go for difference methods like first difference method or second difference method, so that times by default it will be removed. So in the long run, so the impact of intercept is not so important. The impact of slope coefficient is very important, like beta 1, beta 2, beta 3, etc. So obviously we can have this type of model. So now we have y head equal to y head. Similarly, you can create a vector matrix here. Means if you transport this particular equation into this particular format, then obviously where x equal to x11 x21 x31 up to xk1, then similarly x2 21, then x22, then x32, sorry 32, then xk2. Okay, so this is xk2. So this is x12 x22, then xk2. So similarly it will continue up to x1n x2n, then in fact this is x12. Okay, this is x12 x22, then x32 like this. So x1n, then x222 x2n, then x3n, then it will continue xk1. So this is how the x variable is all about. So y is obviously like this, y1 y2 up to yn, and beta equal to like beta 1 beta 2 beta 3. So beta will be like this. So beta will be like this. So beta 1 beta 2, it is in column format. So like beta 2 beta up to beta n. Similarly u1 un you can create. Okay, so this is the basic framework of econometric modeling with respect to multivariate model, or you can say multivariate models by matrix approach. So now I little bit highlight here. So how this error terms will be coming into the picture. So briefly once again I will start with here x beta plus u. So now this is initial setup. So ultimately our aim is to get y head equal to x beta head. Okay, so now what is x beta head here? Beta head equal to x transpose x inverse x transpose x inverse x transpose y. Okay, so this is beta heads, and variance of beta head is beta head is equal to sigma square x transpose x inverse. Okay, then sigma square equal to summation e square by a n minus k, summation e square equal to summation y square minus summation y a head squares. Okay, so this is how you have to proceed. But you remember to transfer this equation to this equations. So that means y means particularly this to these equations. So this is equation number 2. Okay, so means it is the extension of this one. Okay, so that means y head equal to x beta heads, where beta head equal to this much, and followed by next step is to test the significance of the parameters, means all beta. For that you need to have a variance of beta head, and for that you have to have sigma squares, and yes, followed by summation e square y head square. So it is it is the chain how you have to proceed. So, we have discussed long back. So, I am not highlighting in details, but one thing I will like to clarify here is that so the moment you transfer this true model to estimated models, and by the way you are considering that it is the best models which can be used for forecasting and policy use. So that times there is a small issue you have to take care before you directly proceed to forecasting or policy use. For instance, the moment you will transfer from y x beta plus u to y head equal to x beta heads. So now this is the estimated equation, and for that we till now we have discussed about the OLS technique. So by the application of OLS, we transfer this model y x beta plus u to y head x beta heads. In fact, this is simple regression models, and this is estimated models. So now by the way, once you will make difference y minus y head, then you will get the error term. So like, so now e equal to y minus y heads, or sometimes y minus y head. Sometimes it can call as a u head also. Okay, sometimes it can also call as a u head. So u head or e equal to y minus y head. So that is the difference of error term. So now with this basic setup, all these things are absolutely okay, or can be presented here in the form of a modeling. But the thing is, the moment since we are utilizing or using OLS to transfer this original equation to estimated equation, and that model we are considering that is the best fitted model. So obviously it must go through its conditions. Okay, means constant side. So OLS has lots of constants. Some of constants are directly related to x, some of the constants directly related to y, some of the constants are directly related to u, and some of the constant is very generalized in nature. But here our issue is the constants on error term only. So what are the restriction or conditions you have to put for error term before using this estimated model for forecasting or policy use? Okay, so that is our agenda we have to discuss. So now the moment you will transfer this equation to these equations, okay, so then we have already used OLS technique here. So you have used already OLS technique. So OLS technique is based on certain assumption which we have discussed long back, but right now I am just briefly bringing that issue, because that issue will give you the indication of heteroscedasticity. So now if that issue will bring the problem of heteroscedasticity, so we like to know what is exactly the error terms and what are the restriction we can put or we can OLS have in the case of error terms only. So in fact we are not bothering about the general conditions or the condition related to y and the condition related to x. So we are very much interested for this particular heteroscedasticity issue, what is the condition or constraints for this error term u. Okay. So now what are the constraints? So first constraint is E of u must be equal to 0. That means mean of error term must be equal to 0. So that is as usual basic of the statistics, or you can say beginning of univariate analysis. So mean of u means its expected value of u, where we use probability, then we are discussing about the mean issue. So when a simple variable is say x and y, then obviously its deviation is always equal to 0. That deviation is mean in fact. Okay, so that deviation is it may be with respect to true value or with respect to with the attachment of probability value. If it is with respect to attachment of probability level, then we use expected expectations. So obviously the expectation will give you the mean, variance, etc., etc. But like if you go by original issue, so the mean component we put it in or you can cite in the form of average. So when we will calculate average, say mean is one of the standard example. So one of the standard properties of mean is that sum of the deviation of item from the arithmetic mean equal to 0. Like this, for instance, if we have x variables, then we have a standard deviation from x equal to x minus x bar. Okay, so that means summation x should be exactly equal to 0. So x minus x bar should be exactly equal to 0. So the summation x equal to 0 means summation x minus x bar equal to 0. So that there is a statistical proof through which we can get to know deviation of some of the deviation of item from the arithmetic mean must be equal to 0. So since it is a mathematically proof, so you can verify very easily. So the way we are highlighting the issue with respect to a standard variable, say x. So similarly, it can be also applicable for u, because ultimately what is u? U is another variables here. So we start with the y and x. Let's assume that this particular model is based on with the two variables only. So y minus y hat. Let's say y equal to simply beta 0 plus beta 1 x. Okay, so simple this much of information plus u. So this is the means for simplicity we are putting only bivariate models. Okay, so because the heteroscedasticity problem can be discussed under bivariate condition and can be discussed under trivariate condition and can be discussed under multivariate condition. So now we are whatever conditions you are there, so you have to discuss the structure, or you can strategy concepts are almost all more or less same in fact. So that's why instead of going a multivariate problem, it's better to raise this issue in a univariate setup. Okay, so ultimately that will give you path how you have to discuss heteroscedasticity in a multivariate angle. So now what is u here? So like y and x, so we will get y here. So similarly you will get u. So that means altogether there are 4 variables in the system. So I will highlight put it in other way. So let's see here. So y, then x, then y head, then u. Okay, so this is sample information. So sample information says 1 2 3 4 5 6. Okay, let's say 6 only. So then this is y1, this is y2, this is y3, then this is y4, this is y5, this is y6. But remember, y1, y2, y3 are not variable. These are all sample information only. So variable is y. So y1 is the sample for 1 unit, y2 is the sample units of y for second unit, y3 is the sample unit of y for sample 3, y4 is the information of y on sample 4, like this. So it will go to, let's say there are 6 items under y. Okay, so similarly x can be analyzed. So x1, x2, x3, x4, x5 and x6. So initially you have this much of information only. So by the process then we will get y head. So obviously the way we are citing y and x, so obviously y head 1, y head 2, y head 3, then y head 4, then y head 5, then y head 6. So this is how you have to derive. So u equal to y minus y head. Okay, so that means it is y1 minus y1 head, then y2 minus y2 head. So similarly this is small y head 3, then small y head 4, then small y head 5, small y head 6. That is in not small. Okay, y minus y head we are calling it a so small. Okay, it's better not to say y head y3 y4. So you can call it this one. So this is u1, this is u2, then this is u3, this is u4, this is u5, this is u6. Okay, so this is error terminally. Okay, so that means, so y1 equal to this much, y2 is this much, y3 equal to y3 minus y3 head. So this is equal to y4 minus y4 head, then this is equal to y5 minus y5 head, this is equal to y6 minus y6 head. So this is how you will get this particular series. So that means y itself is a variable here. Sorry, u itself is a variable here. So we have 4 different variables. So y, x, y head and u. So our constant is, so y, x, there is a relationship. So how this relationship is means will be getting affected by this error observations. So this is how we will get the errors in this particular issue. So now we are discussing what are the conditions or constants against the error term. So that means, so we have already discussed the constants. Its first constants first is e of u equal to 0. So that is mean of error term must be equal to 0. Second, covariance of ui uj equal to 0 for I not equal to j, okay, and I equal to 1 to up to n, okay, 1 to n. Similarly j can be 1 to up to n, okay. So this is how the entire structure is. That means covariance of ui uj is equal to 0. So you see here, so y x and y head, then then you say u head. So now once u head, then you look at that, let us say this is original u1, so u, then you look at y1 head, u1 heads, then u2 heads. So similarly you can continue, you can say uk head. So like we have discussed a little bit about time series in the last class. So once you have y, then you will go yt minus 1, yt minus 2, yt minus 3, and so on, so on. So in this particular structure can be analyzed similar way. So once you have ut, so you can go with ut minus 1, ut minus 2, ut minus 3, ut minus 4, like this way. Or you can go with respect to ut plus 1, ut plus 2, ut plus 3, like this way. Either it's a past collection or it's a present collection, feature collection, okay. But right now we are discussing about the feature collection. That means, so there are sample observation like this, let's say like this, ut minus 1, ut minus 2, ut minus 3, like this. So it will continue like this. But remember one thing, when we create additional u for given u, then obviously one of the problem you will face is that number of sample size will get reduced, because to maintain the consistency of all the variables at a time. So so you have to find out the appropriate log length, and provided it has to be satisfied with the degrees of freedom. So once until unless you have that, then it is very problem for you. So that means what I like to say, one of the interesting condition for this error correction is that covariance of ui uj equal to 0 for I not equal to j. So in fact this particular problem we have discussed in the last class. That is nothing but the autocorrelation problem. So autocorrelation means there is no such covariance between the error terms, okay. So now a third assumption is that this is all issue. Third assumption is that covariance of ui uj is equal to sigma squares for I equal to j, I equal to 1 to up to n, j equal to 1 to up to n, okay. So that means covariance of ui upon uj for I equal to j means it is nothing but variance of u, okay. It is nothing but variance of u. So variance of u must be constant. So that means, so we have to, so once you have u, so first you check it whether error mean of that error term is exactly equal to 0. This is step 1. So if it is satisfied, then you have to go to step 2. Step 2 means you create additional u2 so like ut minus 1, ut minus 2, ut minus 3, like this. So that means your sample point will be coming like this. This is ut, this is ut minus 1, this is ut minus 2, okay. So if it is coming 1 2 3 4 5 6, then obviously this will be 1 2 3 4 5 5 6, then obviously this will be 1 2 3 4 5 and 6, okay. So 5 and 6. So that means you are losing here one sample, you are losing here two samples, and there is the addition of extra sample. So this side you have to remove, this side you have to remove, and this side you have to remove. So that means, so now the model can be fitted with 1 2 3 4 5. So 5 observation you have to take into considerations, okay, before using second log length. So similarly if you add another variable, then you are going to lose the degree of freedom 1. So that means instead of 5, then you will take only 4 sample points only. So once you add one after another variable, then obviously means with respect to log introduction, then obviously you will lose sample observation. So that is how you must be very careful how much log length you have to consider for a particular problem. So that means the moment you will use the log length, that is nothing but the indication of time series modeling. So one of the standard assumption of the time series modeling is that, so your sample observation should be substantially very high. So if the sample observation is substantially very high, then obviously if we create number of U's within a given setup, then it will not serious problem. But if you have a very small size, a small sample size, then obviously to have more number of U is very difficult. So that's why before you handling this type of problems like autocorrelation and heteroscedasticity, so one of the standard entry point is that your sample observation should be exclusively very high. If the sample observation is very low, then it is very difficult to have the best fitted models, and that means it is very difficult to through this autocorrelation and heteroscedasticity. So typically, okay, so that is how you have to very careful that. So that means variance of U must be here sigma square. So it has to be satisfied. Then fourth condition is that covariance of U upon x, that means it is a linkage with the independent variable. Covariance of U upon x is also equal to 0, because otherwise it will automatically give an indication of like multicollinearity problem. Because what is multicollinearity? So having linear relationship among the regressors. So that means U is also one type of regressor here, because the U is situated or you can say included in the right hand side of the equation. So the moment something is right in the right hand side of the equation, that can be considered as a independent clusters. So obviously, so there may be some collinearity between U and X, but the model requirement is that, or model the system of modeling is that, so whatever variables in your right side, so whatever in the independent clusters, so these variables should be independent to each other. If they are not independent to each other, then obviously there is a multicollinearity problem. First you solve that particular problem, then you have to go for other problems. Okay, because it is a stepwise process. So one problem once you will solve, you will go to another problem. Once another problem will get solved, then you go to another problem. But in the same time, you must be very careful when you will solve a second problem. The first problem which already clarified or cleared, so that can be again added to the another problem. So to that means when you have a series of tests or is a series of constraints in your front, then obviously to clear all these constraints is a very difficult job. So that means you have to go for very optimum condition, or you can say perfect combination where everything can manage in a typical way. Otherwise it will get affected the systems. Okay, so covariance of U upon X must be equal to 0. So these are the standard assumption we are citing in the Wallace technique to have the true regression and true, you can say, estimated regressions. Okay, so that means the model which we have received through Wallace technique, application of Wallace technique, can be used or can be considered as the best after after confirmation from the specification test and also diagnostic test, and let us assume that it is also confirmed from the autocorrelation and multicollinearity. Still that model cannot be used for you can say forecasting or policy unless you check the heteroscedasticity issue, because heteroscedasticity is a serious problem. Heteroscedasticity very theoretical meaning is that it is heterogeneous in nature. So, but generally, so far as a cluster analysis requirement is that objective is that so the model will be perfectly okay if your sample units are very homogeneous in nature. That is how clustering analysis has a lots of utility in this econometric modeling. So you must be very careful about that particular issue. Okay. So this is the structure how to means these are the conditions you have to cite before using the estimated model for goodness fit or specification test, or also for use of forecasting or policy use. So now here the game of heteroscedasticity will start. So generally if this is the case, there is no such problem. This is by definitional problem. When this is the problem of autocorrelation, this is the problem of heteroscedasticity, and this is another way of representing the multicollinearity issue. So that means this particular problem is more dangerous, and this particular problem is also more dangerous. So in the time this multicollinearity issue we have already discussed, and this is also we have discussed. So now this particular problem we have to highlight in a broad way. Okay, so that means with a given setup given setup, once you apply Wallace technique, you will get the estimated model. Once you get the estimated model, so you have to go for lots of tests before you assume that this model, or before you cite that this model is considered as the best. So for that you have to clear through specification test, goodness fit test, then again to solve the multi-collinearity issue, to solve the autocorrelation issue, and then you will come down to heteroscedasticity issue. So once it will pass, then you have to go for any other problems. But these are the standard tricks how you have to follow before you move to any other problems, okay, directly. So now you see here, so how is that particular setup? So that means you see here, so what is heteroscedasticity issue? So out of we have cited altogether 5 different assumptions. So now if you go through that 5 cited assumption, then one such assumption is very typical integration with this particular component, that is heteroscedasticity issue. So that means, so we have cited one of the condition is that covariance of ui uj equal to sigma square for all I equal to j and I equal to 1 to up to n and j equal to 1 to up to n. Okay, so this is how we have highlighted. So now now you see here, so this is sigma square means it is a constant. This is not sigma, it is called as a sigma square. Okay, so generally we use sigma square u instead of writing sigma square, we can use sigma square u. That means it is the moment you will put sigma square u, it is an indication that it is a error variance. Otherwise I can write sigma square x, sigma square y, it is a variance of standard deviation of yes, sigma square x means it is a variance of x, sigma square y means variance of y. So similarly sigma square u, it is a variance of u. So the rule is that the variation should be a constant over the error terms. Okay, so there may be some variations in the sample points, but here there should be a constant variance. If the variance is not constant, then obviously it will go against the system of econometric modeling. That true typically for this heteroscedasticity issue. So now if by any chance if it is done or if it is obtained, then that means there are 2 questions here, yes questions and no questions. So that means this is one of the assumptions. So now if it is assumption, then by default it will turn into a hypothesis. So hypothesis is that, so covariance of ui uj equal to sigma not equal to sigma or equal to sigma square u, and against the alternative hypothesis that covariance ui upon uj is not equal to sigma square u. Obviously sigma square u is always there. For instance, if you will integrate u1 with u2, you will get sigma square. If you u1 means u11, then u22 like this, where the clustering will be in a diagonal setup like this. You see here. So what is error? Means error variance matrix, variance covariance matrix. So you see you have u first, then you will create first u equality u1. Okay, so then u2, so another variable u3, u4, u5. Okay, so let's say this is un. So similarly you have here u1, u2, u3 up to you have un here. Okay, so now we like to prepare a variance covariance matrix. We like to prepare a variance covariance matrix. Okay, so this will give you indication of, means this particular matrix will give you signal for autocorrelation problem, and it will give signal for the heteroscedasticity problem, or you can say homoscedasticity problem. Homoscedasticity is the counterpart of heteroscedasticity. So now by the moment you will say variance covariance matrix, then obviously we can prepare like this way. So it is nothing but u1 squares. Okay, this is u1 u2, then this is u1 u3, this is u1 u4, then this is u1 u5, then it will continue u1 un. Alright, so this is first component. Then similarly u21 u2 u1, u2 squares, u2 u3, u2 u4, then u2 u5, then it will continue u2 un. Okay, similarly u3 u1, u3 u2, then u3 u2 square, sorry, u3 u3, okay, then this is u3 squares, okay, this is u3 squares, then u3 u4, then u3 u5, then continue u3 un, okay. So similarly un1 un u1 un u2, then un u3, then un u4, then un u5 un squares, okay. So this is how the complete variance covariance matrix, where there are n number of error terms. That means we start with a single error term, say u1, then you will create several error terms u2 u3 u4 u5 up to un. So now if you put a time series aspect, then it will be start like this: ut minus 1, ut minus 2, ut minus 3, up to you can say ut minus k, okay. So now if you say k means t equal to t minus k, so depending upon the value of k and t, so the error term can be evaluated. So the evaluation is like this: u1 u2 up to un, and this is u1 u2 up to un. So now if you multiply vertically or horizontally, then obviously you will get this particular matrix. So now this particular matrix has a 3 different shapes. There are 3 different shapes of this particular matrix, okay. So like this. So now this u3 u4 will come here only, okay. u3 u4 will come here only. So this is the diagonal matrix you have here. So that means this is the diagonal elements. That means you have 2 different matrix. So one is the off diagonal, and this is on diagonal, this is off diagonal, this is diagonal. So that means I 3 different setups. One is the diagonal elements, then off diagonal, on diagonals and off diagonals. So these are symmetric in nature. For instance, u1 u2 is nothing but u2 u1. So similarly, if you have this much of information, then automatically you transpose it and paste it here, then you will get this particular matrix, okay. So you remember here, so this side off diagonals and on diagonals are more or less same. So because it will give you the situation where for off diagonal and on diagonal, then covariance of ui uj is equal to means as per the conditionality it should be 0 for I not equal to j, okay. So when u1 u2 is there, then obviously I not equal to j. So when u1 square is there, then it is the case where I equal to j, but the starting is the covariance of ui uj. So when ij are equal, then you will get diagonal elements. So when you will get I not equal to j, then either you may be in off diagonals or you may be in the on diagonals. So that is depending upon the situation. So now if you are here or you are here, then this particular problem is called as a autocorrelation problem. So if you are in the off diagonal and on diagonal, then you are in the this is autocorrelation problem, and this is heteroscedasticity problem. This is heteroscedasticity problem, but we have not highlighted what is heteroscedasticity here. But autocorrelation you can directly get to know, because it is the covariance matrix, not variance matrix. But so accurate issue of autocorrelation and heteroscedasticity is that you see here. But be careful one thing here. In fact, this autocorrelation, like there is lots of connection between multicollinearity and autocorrelation. There is also similar in the similar way. There is also some kind of similarity in the case of autocorrelation and heteroscedasticity. One of the similarity is that, so the problem is discussed under the condition of error terms only. Basically, there may be some it is definitely has an integration with a dependent variable or independent variable, but the root is the error term for both autocorrelation and heteroscedasticity. So now after having the variance covariance matrix, so that will not give you clear cut indication of heteroscedasticity issue. To get the clear cut indication of heteroscedasticity issue, so let me highlight here what is exactly that one. So the transformation matrix is like this. So u1 u2 it will u3 it will continue like un, then this side you will continue u1 u2 up to un, okay. So now this is this is sigma square means u1 square. So we will call it is sigma square 1. Okay, this side we will call it is sigma square 2. So this side we will call it sigma square 3. So it will continue, then you will get sigma square n. Okay, so this is called as sigma 1 2, sigma 1 3, then sigma 1 n, then sigma 2 1, then sigma 2 square, sigma 2 3. So it will be sigma 2 n. Okay, so sigma n 1, sigma n 2, then it is sigma n square. So this is how the matrix all about. By default, this should be unit, say sigma square. This should be equal to sigma square. This should be equal to sigma square. This should be equal to sigma square. Okay, let's say unit means it is just like the case of unit matrix. When we will go for matrix algebra, then it is the structure means OLS technique condition is that the error variance covariance of variance covariance of error matrix must be must be equal to the unit matrix. Okay, so what is mean by unit matrix? The matrix unit matrix has two interesting properties. First thing is the elements are square in nature, means row and column will be same, like 2 into 2, 3 into 3, 4 into 4, 5 into 5, n into n. So that is the matrix. So that means matrix must be square and the value of matrix must be exactly equal to 1. So how do we get value of means this type of matrix? That means in all diagonal elements the value must be exactly equal to 1, and other diagonal elements the value must be exactly equal to 0. So that is the representation of unit matrix, and in fact in econometrics that is the requirement of OLS application. Means one of the standard assumption of OLS is that so the error matrix, error component matrix, I mean that to variance covariance matrix should follow the unit matrix set. That means so this will be transferred to like this way. So this is 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. So this is the case like this way. This is the case like this way. This is 1 2 3 4 1 2 3 4. So this is 4 into 4 matrix. Okay, this is 4 into 4 matrix. So that means we are just considering u1, u2, u3 and u4. Okay, we are not going up to n term. So now as usual I have mentioned, so this particular term is 1 1 1 and other terms will be 0 0 0. That means you can connect here. So sigma square 1 is this much, sigma 2 square is this much, sigma 3 square is this much, sigma square this is another is sigma square 3 sigma square 4, this is equal to sigma. So this will connect to this one. So okay, this is how if this transformation, this means this value of this particular matrix will be like this, then it is called as a homogeneous issue. It is called as a homogeneous issue, or it is otherwise called as a homoscedasticity problem. So means this particular, if means we are directly targeting the diagonal elements after the value of that particular matrix, means quantitative figure of that particular matrix, not value of the matrix. Value of the matrix means the value of the determinant must be exactly equal to 1. So we are not, obviously if you will get this type of matrix, then value is always equal to 1. That is how it is called as a unit matrix. So that means the value 1 means it is the value is unit only. So if that is the case, then there is no such heteroscedasticity problem. But if all are not following the unit root matrix, singular matrix, or matrix having the value is 1, so unit matrix, then obviously then there is a problem of, you can say, homoscedasticity. So that will lead to heteroscedasticity. So that means our requirement is a homoscedasticity. If not homoscedasticity, then obviously it is a heterogeneous heteroscedasticity problem. So obviously the presence of heteroscedasticity is not good sign for the econometric modeling. So you have to bring the heteroscedasticity issue to homoscedasticity. You may not get exactly the homoscedasticity issue, but you have to be very close to homoscedasticity. That means error variance should be, by default, should be very equal for each and every sample structure. Alright. So now if it is 0 0 0, then that means this will be connect to this one, this will be connect to this one, this will be connect to this one. So like this. So similarly this one connect to this one, and then the sigma n1 connect to this one, sigma connect to this one, like this. So this is how the variance covariance of matrix. That means the off-diagonal elements and on-diagonal elements for this variance covariance of error matrix is equal to 0, then obviously it is called as a autocorrelation problem. That means it will give you indication that there is no autocorrelation problem. Again, similarly, if the diagonal elements are giving the signal of 1 1 1 1, then it is giving a green signal that it is the homoscedasticity problem. That means there is no such heteroscedasticity problem here. So the moment you will get covariant off diagonal on diagonal elements are all 0, then it by default it give a signal that there is no autocorrelation problem. Then again, if the all diagonal elements are equal with respect to all sample size, then it will give you the green signal that there is no such a heteroscedasticity problem. So now we have a various questions here. So issue is what is all about this heteroscedasticity. So means with this basic introductions, so now we will highlight what is all about the heteroscedasticity issue. So that means we have now number of questions. Okay, what are the questions? We have number of questions. First is what is heteroscedasticity exactly? What is heteroscedasticity? Okay. Then second, how is its nature? So how is its nature? So this is the second aspect of the problem. Third, what are the causes? What are the causes? Fourth, what are the consequences? Consequences. Okay, so what are the consequences? Then fifth, detection criteria. Okay, detection criteria. Okay, what are the detection criteria? Sixth, is it a problem? Is it a serious problem? Is it a serious problem? That means the question is the presence of heteroscedasticity, is it a serious problem? So that we have to highlight. Okay, that means automatically it will give connection to consequences. Okay, so obviously the consequences, the moment you are saying consequences means what are the negative impact on the presence of heteroscedasticity. Once if it is some positive impact, then there is no problem. Okay, but if it is a negative impact, then obviously you have to remove this negative impact. Okay, so is it a solution for this particular, means is it a solution for the presence of heteroscedasticity problem? Seventh, the solution for heteroscedasticity. Solution for heteroscedasticity problem. So that means you remember when we are talking about solution to the heteroscedasticity problem, then obviously by default heteroscedasticity you can say means it is a negative impact on econometric modeling. So you need to have its detections. Okay, so that means we need to have detection and you need to have its solutions. Okay, so now next issue is you have to clearly highlight what is exactly the heteroscedasticity. So that means first point is we mentioned what is heteroscedasticity. You see here, basically heteroscedasticity divided into two parts. One is called as a hetero, then scedasticity. Okay, like homoscedasticity, this is homo and scedasticity. So this is heteroscedasticity, hetero and scedasticity. Hetero means it is unequal variance. Okay, this is hetero represents unequal. Okay, unequal. So homo means it is equal. Homogeneous means it is equal. For instance, suppose there are three products are there. So I like to be keen on quantity. So 10 10 10, that is how it's in a homogeneous in numbers only. Okay, it may be different weight, it may be different color, it may be different size, but number wise 10 10 10. So this is one type of homoscedasticity issue. Or other else like this, it may be 10 15 20, but color wise it is same. Okay, so that means it is just like you are sending one market this 10, another market this 10, 15, and another market this 20. So but the color is the same. So this is how it is can be homogeneous in nature. So homogeneous can be various angle and heterogeneous can be under various angles. Like if you put the same thing in a heterogeneous issue, so that means let's say there are three different products, then this is 10 greens, 10 yellow and 10 reds. So that means we have to pick up something, 2 from here, 3 from here, 5 from here, then it will go to one particular market. Then rest 3, 6, 7 will go to another market, and the rest of the items will go to the another market. That means number wise it is hetero, then it is color wise it is hetero, then market wise its classification is also hetero. So this is how the heterogeneous issue is all about. So scedasticity means it is spread of error variance. It is the spread of error variance. It is the spread of error variance. Okay, so heteroscedasticity is a two aspect, hetero, unequal, and scedasticity means spread of error variance. So now if you will integrate these two, then obviously it will give you the signal of it will give you the signal of unequal error variance. It will give you unequal error variance. That means, so we need sigma square u, but now it cannot be operate. So it will be it cannot be u. It will be like that, sigma square u I. So that means I 1 2 3 4 like this way. So that means the structure we have created here, sigma square 1, sigma square 2, sigma square 3 like this, sigma square n, sigma square n, it is not equal, not equal, not equal, not equal. So this is how the heteroscedasticity all about. Okay, so means the definition says that heteroscedasticity means the spread of unequal variance in the system, econometric modeling system. So if the error variance are unequal over each and every sample points, then obviously this is a serious problem for econometric modeling. So that has to be taken care first before you use this model, or before you can say assume that the model is the best fitted. So it is used for policy use, or you can say forecasting use. So first heteroscedasticity has to be removed, then you have to go for use a forecasting or policy use. With this we can conclude this particular session. Next class we will highlight the detailed setup, the causes, consequence, detection and its solution. So with this we have to finish this lecture. Thank you very much. Have a nice day.